Yesterday, we talked about what happens when a wave encounters a boundary between two different materials, two different media, we call it. And the demonstration that we did yesterday involved a slinky and, well, first of all, it involved a slinky and a hand. Okay, two different materials, clearly a slinky and a hand. And then secondly, it involved slinky and air. Again, clearly two different materials. And we found that when a wave encounters that boundary, you're always going to get two things happening. There's always going to be some of both of these things happening. The first thing that's going to happen is transmission, where the wave keeps going. And the second thing that's going to happen is reflection, where the wave bounces back or is reflected. When Ollie was our volunteer up here yesterday, and we sent that slinky wave down towards Ollie's hand, and it reached the boundary between the slinky and the hand, we found that most of the wave was reflected, but a little bit of it actually did keep going. Right? We saw Ollie's hand move a little bit, so a little bit of the wave was transmitted, but most of the wave was reflected. The reason that most of it was reflected and only a little bit was transmitted is because those two materials, the hand and the slinky, were very different from one another. So when two materials are very different, we get mostly reflection. But when two materials are very similar, we get mostly transmission. If we were to do like, remember the old game Red Rover? And you're holding hands with a bunch of people, okay? And we were to make some kind of sound that was transmitting through people, which can actually happen, right? Sound transfers through your jaw. You guys ever listen to yourself on recording? You guys ever listen to yourself like on tape? Do you think you sound stupid? Yeah. Well, let me tell you, that's really the way you sound. That's really the way you sound. That's the way you sound to other people. The reason you sound different to yourself is because when you're talking to other people, the sound goes through air to their ears. When you're talking and you're listening to yourself, sound goes through air to your ears, but it also goes through your jaws to your ears as well. Sound transfers through your body, through your facial bones, your jaw, and so on, which makes it sound a little bit different than it does when somebody else is listening to you and the sound goes through only air. So you get these people holding hands playing Red Rover. There's some sound that's being transferred through people. And every time it reaches a boundary between people, okay, different media, there's going to be some transmission and some reflection. We're going to find that in that case, it's going to be mostly transmission because one person holding hands with person number two, those materials aren't very much different. It's not like slinky and person, where they're very, very different and most is going to be reflected. Person and person are very similar, so we're going to get most of the wave transmitted with only a little bit of reflection taking place when it reaches that boundary between the two people. Now, we're going to focus right now on just the part of the wave that's reflected. Remember, you always get some transmission. Sometimes it's a little bit of transmission in the case of the two materials being very different. Sometimes there's a lot of transmission in the case of the two materials being very similar. We're only focusing on the part that's reflected right now. And two things can happen to the part of the wave that's reflected. Number one, it can be reflected right side up, or number two, it can be reflected upside down. You guys saw yesterday in the demonstration that when the slinky was attached at the other end, so Ollie was holding on to the slinky, then we found that the wave was reflected upside down or inverted. So if something like a slinky is attached at one end, you will get a wave that's reflected upside down or inverted. You saw with the demonstration in the atrium, when we went from slinky to air, and it wasn't attached to anything, you saw that it was reflected right side up. So we're going to say that it's reflected upright when it's not attached. Well, sometimes we don't really have an attached or not attached thing. Sometimes we're dealing with something like air and water. You can't really say is it attached or not attached or whatever. So we have another way of describing it as well. The wave is reflected on the same side when it's not attached, or we can say that when it's going from more dense to less dense. So when you're going from slinky to air, slinky is more dense, the air is less dense, then the wave is going to be reflected, or at least the portion of the wave that's reflected is going to be reflected right side up. because you're going from more dense to less dense. On the other hand, when you're going from less dense to more dense, that was when you were going from slinky to person in the demonstration yesterday, we found that the wave was reflected upside down. So if you come across a situation where it's clearly attached or not attached, like a slinky, then use that as your rule of thumb to determine whether it's going to be right side up or upside down. But if it's more like air and water or air and some other gas, and you want to know whether the wave is reflected right side up or upside down, then you got to look at the density. Okay, and you'll be told, oh, the density of this medium is higher, or the density of this medium is lower than the density of that medium. Well, what if it's reflected, or what if it strikes the boundary at an angle? We couldn't demonstrate that yesterday with a slinky. It had to be hitting the boundary straight on. But what if it's not straight on? What if it's hitting it at an angle? What if this is our boundary and the wave is hitting it like this at an angle? Well, what we're going to do is, first of all, draw what we call a normal line. Normal in physics means 90 degrees. Normal force, the force at 90 degrees. Normal line, the line drawn at 90 degrees to the boundary. We're going to measure this angle right here. We're going to call it theta I, the angle of incidence. We're going to observe what angle it reflects off at. And when we do, we're going to measure that. And when we measure that, we're going to find that the angle of incidence, the angle that it strikes the boundary at, as measured from the normal line, will be equal to the angle of reflection, as measured from the normal line. That's called the law of reflection. And we've seen that law before, right? We at some level, we know and we understand that law before I even tell you that. If you're hitting a pool ball off the bumper of a pool table, you know roughly what angle you have to hit it at in order to get it to the place that you want to get it. Right? You have to hit it such that it bounces off at the same angle that it struck it at. The angle of incidence equals the angle of reflection for the reflected portion of the wave. But what about the portion of the wave that doesn't reflect? What about the portion of the wave that's transmitted, that keeps going? Again, we know that we always get some reflection in some transmission. Sometimes just a little bit of transmission, sometimes a lot of transmission. But regardless, there are properties of that transmitted wave that we haven't identified yet. When we get transmission, we're going to find that some things, some of the properties of the wave will always change, and some of the properties of the wave will never change. We will find, first of all, that the speed of the wave will change. If a wave is going from water to air, let's say it's light, a light wave, and it's going from water to air, the wave will speed up. But it's going from air to glass, the wave will slow down. When we're going from one medium to the other, when we look at the transmitted portion of the wave, it will always either speed up or slow down. It'll always change speed one way or the other. As a result of that change in speed, the wavelength will change. If the speed of the wave goes up, then the wavelength of the wave will go up. If the speed of the wave goes down, then the wavelength will go down every time. And finally, the direction, I'm going to star this one, because the direction can change, but not necessarily. If the wave comes straight on to the boundary, then it's going to keep going in the same direction. But if the wave goes at a certain angle from the boundary, then it's going to go through, it's going to transmit, but it's going to transmit at a different angle. It's going to change direction. Speed and wavelength always change. Theta will change if there's a value of theta other than 0. What stays the same? We talked about this yesterday. What always stays the same? The frequency. Although it may slow down or speed up, although the wavelength may change, the number of cycles per second of that wave will not change. And you're going to see the relationship between all of these things here in just a moment with an analogy that I want to give you. Let's say we've got, it's a little bit of a strange analogy, but I think it will illustrate nicely what we're trying to show here, okay? We've got a parking lot here, and this parking lot is paved. So we've got pavement on one side of the parking lot, and on the other side over here, we've got a swamp, kind of a swampy area. It's the edge of the parking lot. Maybe the restaurant is over here, and the edge of the parking lot, it's a swamp beyond there. They don't need to, big enough parking lot, they didn't need to pave into that. Now, for whatever reason, we got soldiers marching in this parking lot. I don't know whether it's parade day or whatever the case may be, there's soldiers marching in this parking lot. And these soldiers are all lined up, ready to go for this parade like this. If we look at them from above, then the wave front, if we kind of visualize this as a wave, would look something like this. So, I don't know, maybe it's parade day, maybe there's a helicopter circling above from the news, and they're taking video of it or taking pictures of it, and this is what they see. These soldiers all lined up, looks like a wave front because they're really close together. Now these soldiers start marching. When they start marching, of course, you know what soldiers do, right? They march in stride. They all march at the same speed, the same pace, the same distance. Perfect, right? So a couple seconds later, the soldiers are up here. They're not where they were before. They've marched up here, except this poor guy, who's now in the swamp. So this poor guy hasn't marched as far. How come? Well, how come he hasn't gone as far as the rest of the guys? Good. The swamp is harder to walk through than the pavement, so he's going to slow down. The speed has changed. Now, what does this look like from the news helicopter above? It looks something like this. Okay, let's fast forward a couple seconds again. And these soldiers are marching like this, except now there's two guys in the swamp. So now from the helicopter, it's going to look something like this. A couple seconds in the future again. Now you got more guys in the swamp. And the wave front looks something like this. What do you notice about this? First of all, fundamentally, the most important thing is when we went from one medium to another, these soldiers transmitted, right? They went from one medium into another. When they did that, their speed changed. That's the most important thing here. Okay, when you go from one medium to the other, the speed will always change. Now, other things that change because of that, because of the speed changing. For instance, the wavelength. Look at the wavelength here, the distance between crests. Look at the wavelength here, distance between crests. The speed has decreased dramatically in the swamp. The wavelength has also decreased dramatically in the swamp. Make sense? What else has also changed? Well, the direction. The wave front, gentlemen, was like this. It was going north, and now the wave is going like this. The direction has changed as well. Now, if these soldiers had encountered that boundary like this, then those soldiers would have slowed down, and they would have changed their wavelength proportionately to the speed, but they wouldn't have changed direction. They only change direction when they hit it at an angle as opposed to straight on. That's why we said theta is starred. Theta sometimes changes, but not always. What doesn't change? Well, we had, once it goes into this medium, we have 3 waves that have occurred after it went into the medium. We have 3 waves in a certain amount of time here. We have 3 waves in a certain amount of time here. If we have the same number of waves in the same amount of time, then what hasn't changed? The frequency hasn't changed. The frequency will stay the same. Doesn't matter what happens here, guys. Even though the speeds changed, the wavelengths changed, the angle changed, the number of waves that we have per unit time doesn't change. Once a wave has been made, the frequency stays the same. Make sense?